Hi students, welcome back to geology. Today we are talking about surface water. All right, so everyone needs water, obviously. It's essential to all life on Earth. Without water, we wouldn't have any life on Earth. It is our most valuable resource, and it's basically considered liquid gold at this point because of all the water rights and everything that people are trying to get a hold of the very limited resources that we do have. So water is essential to your body, right? So 60% of your body is actually water, and you can only really survive a few days without water, but you can survive weeks without food. Although your stomach will try to tell you otherwise, technically you can survive quite a while without food, but not without water. So water is everywhere, as you've probably noticed on the surface of our planet. There is 70% of Earth's surface is covered in water. But we have a huge problem with that. Only about 1% of it is actually usable water. So 97% of the Earth's water is actually in the ocean. 2% of that is, of the 70%, is in glaciers and locked up in polar ice where we can't actually do anything with it. 0.62% is in groundwater, which is where the Central Valley gets all of its water. And 0.008% is in lakes and rivers, 0.001% is in the atmosphere as water vapor. So we have this huge issue where we only have about 1% that we use for absolutely everything. So that 1% we use for drinking water, we use it for agriculture, we use it for transportation, we use it for steam power, and lots of other things, right? The most important to us might be drinking water and agriculture. So based on that, who uses the most? We might think that it's drinking water or maybe steam power, but it's really agriculture. And in the Central Valley, it's pretty obvious that it's agriculture. So if you look at that graph in the upper right-hand corner, it shows that ag uses the most amount of water, and then it's domestic use. So then it's drinking. And then after that would be industry, so steam power and things of that nature. If we were looking at petroleum here, we would really be looking at kind of an opposite situation where industry would be using the most, and then domestic is probably still in the middle, and then ag. But when we're looking at water, we're looking at agriculture, and they are using a lot of water. So you can contribute to water, saving water and water usage by controlling what you use in your home and what you use when you're out on campus or you are out and about in the world. So you can actually go to this website and calculate how much water you're using in a day if you are interested, if you're not sure how much you're using. But there are a few things in your home that are using more water than others. So that would include the toilet. So flushing uses quite a lot. And then your laundry uses quite a lot. Obviously, people don't always think about it when they go to the bathroom or they're washing their clothes, but it does use a significant amount of water to run through a cycle, and especially if your washing machines are not energy efficient, they're going to use a lot more water. Some of the older machines use a lot more water than they really need to. I noticed when I switched to a more energy efficient washing machine that my clothes are not nearly as soaked as they were when I was using like a really, really old washing machine. But you are very lucky that you live in an area where you can access what we call potable water or potable water. And potable water is anything that's drinkable, right? It doesn't have any significant contaminants in it, and it is safe for drinking. There are lots of people around the world that have to go several miles every day to go fetch water from outside where they live. But if you turn on the faucet, in particularly anywhere in California, you have access to clean drinking water. It is California state standards that the water that comes out of a tap is completely drinkable. It's completely potable. I know a lot of people don't like the taste of it, but it is safe for you to drink. There is nothing in it that is going to harm you. So I've been drinking tap water since I was little, so I don't have a problem with it. I know Fresno has a lot more chlorine in it than where I grew up in the country, but tap water is perfectly safe for you. You don't need all of this filtered water all of the time. But all of our consumption is drying up all of our freshwater systems, so we are losing a lot of water on the surface. And the Aral Sea in Kazakhstan and Uzbekistan is a really good example of this, where we can see in just aerial footage in the last 40, 50 years that we have depleted this freshwater storage significantly. So there's an image under A there showing you September of 1977, excuse me. And then in the bottom right, it takes you all the way to June of 2013. So we've had significant depletion of this freshwater storage. And unfortunately, when this happens, as water is evaporated and removed very quickly from this water source, we see the deposition of salts. So if you remember from sedimentary rocks, we talked about evaporites. So all that white there that you can particularly see starting to form in E in June of 2009, all of that white is evaporites. And all of those evaporites are going to be really high in salt concentration. So even if water was reintroduced to this area, it's going to be really high in salt, which is not something that is safe for humans to consume long term. Okay, so this depletion is really causing or wreaking havoc on our surface water systems. And unfortunately, in this case, replenishing here is not necessarily going to be an option because of the salt content. So that's not to say that the water is disappearing, right? So a lot of people don't really understand how the water cycle works, where the water is just being trapped elsewhere. It's just not somewhere where we can use it. So it's either in the ocean or it's in a bunch of people. We are part of the water cycle, right? We're animals, we consume the water, and then we let go of the water. And so our wastewater is something that we could be looking into to clean up and refilter so that it could be reusable before it goes back into lakes or streams or back out to the ocean and we can't use it by then. So we have some basics here, right? We have evaporation, we have condensation, and then precipitation. Most of us kind of know all of those basics. But once the precipitation hits the ground, that's where we want to figure out how we can capture it. Is it gonna run off? Is it gonna infiltrate? Is it going to run off into the ocean? What is going to happen to it? And so at the end of this PowerPoint, we will talk about infiltration and what we can do to kind of help things infiltrate better so that we replenish our groundwater and we actually use that storage instead of just continuously deplete it. All right, so surface water, like I mentioned a little bit ago, is water that is on the surface. So it's not absorbed into the ground yet, although we will talk about some surface water groundwater interactions in the next lecture when we talk about groundwater more specifically. But this is any water that is in our streams, our rivers, or our lakes. So as water is moving, we talked about with sedimentary rocks that sediment is moved by water pretty frequently. And in a river system, there are a couple of ways that water can move the sediment, and that is in solution, in suspension, and along the bottom of the channel. So along the bottom of the channel is pretty common. You can kind of see that here in this little video. There are rocks or little pebbles that are moving downstream just on the bottom of the channel little by little. In suspension is in the water column. So these are smaller particles that are closer to the density of the water and are being moved by that water column in suspension, basically. And then dissolved load or in solution is particles that are so small, they are moving with the water molecules. So these are teeny tiny little pieces of sediment that are moving basically in solution. All right, then we can look at stream velocity. So stream velocity is controlled by these three factors. One being gradient, so the steeper the gradient, the steeper the hill, the faster the water is going to move. So the water is not going to move very quickly if it is a flat area. So through the Central Valley, the water doesn't move super quickly because the gradient isn't very high. Channel smoothness. So the smoother the channel, the faster the water technically can flow. Now the problem here is a lot of the time is the channels that are high up in the mountains are very coarse, and there's a lot of big boulders that the rocks have to move over, and it does look like the water's moving faster, but it's really the gradient that's controlling that there. Whereas when you get down into a valley, the water can technically move faster because the channel is smoother, but it is not a high gradient there, so the gradient is slow, so the water slows down a little bit. But technically, if we had a steep slope but a smoother channel, it's going to move faster than a rougher channel. And then the size and shape of the channel is also going to impact stream velocity, because if your stream channel is really wide, the water is going to go outward first, and so it's going to spread out towards the sides laterally and then move downstream. If the channel is really narrow, then you're going to see a faster flow in that center part there. Looking at some of the largest rivers by discharge, these are the top 10 on the earth, Amazon being the largest, and by a lot, right? So Amazon, and then the Congo River is behind it, and there's a significant difference in the amount of discharge. So that CFS there is cubic feet per second, and that's the water output at the mouth of a river. Okay, and we only appear on there with the Mississippi River, so we did make it, but we don't have nearly as large of river systems as some of these other countries around the world. All right, looking at some stream types. There are two basic types. We have braided and we have meandering. Braided streams are streams that have inner network of channels, and this network of channels is mostly impacted by the amount of sediment that's present. So there's lots of sediment here, and water is just trying to find a way to flow downhill. And a lot of times this is near a glacier. So where there's not a developed river system and a glacier is just melting and there's just water running off, and we see a lot of different channels that this river or the water is finding in all of the sediment that the glacier is also leaving behind. And then with meandering streams, these are streams that flow in a series of bends just back and forth through the landscape. Okay, so with braided streams, here, like I said, we're looking at a lot of small single channels that kind of make this overall network, and it kind of looks like a braid as the water is moving through the sediment. Again, there's a high sediment load here, so this is somewhere where lots and lots of sediment has been deposited, and we have water also involved trying to maneuver through all of that sediment. Right, and then we have our meandering stream, which is a single channel that winds through landscapes. And so you'll see something that looks kind of curvy, and so here is the big bend in the Grand Canyon where the Colorado River is making its way around this, and I'll show you what happens when curves get so tight like this that nature just doesn't really want to work with us anymore. All right, so meandering rivers show water flowing through landscape and carving paths. And so what happens here is as the water comes around a bend, it tends to dig into the sediment and it cuts into the bank of the river. And so we call that the cut bank. And the cut bank is the erosional feature on a meandering river. Now, with a meandering river, a meandering stream, there is going to be numerous cut banks. It's not just one. It's on the outside of every curve where water is the fastest. So if you look at the diagram on the bottom there, it shows you where fast flow is and where slow flow is. So as it goes around a curve, there at B, you can see that there's a faster flow on the outside of the curve, and on the inside, it's slower. On the inside of the curve, we see a lot of deposition of sediment, and we call that the point bar. So a point bar is a depositional feature, and a cut bank is an erosional feature where material is being removed, deposition, material is being left behind. Okay, so other things that also are formed here are things like oxbow lakes and meander scars. And so let me show you how an oxbow lake is formed. So as a river is snaking through the landscape, we start to see a lot of bends become curvier and curvier. And as they become more and more curvy, they start to bump into each other. And so when those curves bump into each other, the water goes, wait a minute, I'm going to take the easier path. I'm going to take the straighter path. And so the water takes the straighter path through the landscape, and it leaves behind that curve. That curve that's left behind is known as an oxbow lake. Problem with oxbow lakes is they don't have any water coming in and out of them, right? Unless it rains, the water's going to continuously evaporate or infiltrate. Okay, so as that happens, it starts to turn into an oxbow swamp, and then we're left with a meander scar in the landscape. So if we look at a river system, you can see around, particularly at the bottom right there, you can see some meander scars that are left. You can see some of the curves that are getting so sinuous that they might cut off at some point. And so this is how these systems work. They snake through the landscape and every so often cut itself off so that it becomes a little bit more productive and not having to snake super far out of the way and then back around. All right, moving on to drainage patterns. When we're talking about the way that water is moving, we have 4 basic drainage patterns. So this is all just surface water still. Dendritic, radial, trellis, and rectangular are the 4 basic types. So first, looking at radial drainage. So radial drainage comes from a single point and goes down. So this is oftentimes a single peak. So it could be a volcano or it could be just a single peak mountain, and the water that comes off of it radiates from a central point. Okay, so if it is a depression, so a low point, it could also radiate inward to a central location and fill that up. So in some sort of bowl-shaped feature or a basin, you might see radial drainage coming towards the center, and then with a mountain peak, you would see it come from the center. All right, looking at rectangular drainage, this is where we have a lot of very blocky rock. So this rock is usually breaking in a very rectangular pattern, and so the water follows those crevices and those cracks in the rock, and so we see this very rectangular type of drainage. With trellis drainage, we are looking at a bunch of small tributaries that are feeding a single tributary in the center. So we have resistant rock and then water that is coming off of those rocks, and then it's meeting a central point and then going down slope. So we're usually seeing a 90-degree angle between the smaller tributaries and the main system that is flowing downhill. And then lastly, we have a dendritic drainage, which is a pattern of water flowing in a very homogeneous rock, so rock that is weathering pretty evenly, and it generally resembles this, what looks like a dendrite in a brain, which is where the term comes from, but it looks like a series of branches from a tree or veins in a leaf. These are very common in our deltas. We see a dendritic drainage pattern. All right, surface water, infiltration, and runoff. So like I said before, our number one thing is we want it to infiltrate. Runoff isn't always so good because it ends up somewhere where we can't use it. So water runoff can come in a couple of different forms. It can be our rivers, it can end up in our lakes. We might see small streams and creeks. It might be storm drainage if we're in an urban area, and then sometimes it can cause flooding. So we deforest or we do construction, we're losing a bunch of vegetation, and the vegetation helps with infiltration. And so if we deforest a bunch of areas, we're just going to see a lot of runoff, and that runoff is going to also take loose sediment with it, which is a problem. Okay, so some of the factors that improve or change the amount of water infiltration we see is precipitation, so how much water we're getting, the base flow, so what water is already on the surface. If it's already saturated and there's water on the surface, there's not going to be as much infiltration. Soil characteristics, so is your soil got a lot of room to spare water or not? The saturation of the soil, so is the water or the soil already saturated with water? More water can't fit if it's already saturated. Land cover, so what's on the surface. And then slope of the land, so if the slope is really high, infiltration won't happen very much. It's going to run off before it has time to absorb. And then evapotranspiration, so that includes the plants and the trees. We want to make sure that there's more of them there so that it can actually infiltrate. Okay, so 2 factors in the soil impact the water infiltration, and those are porosity and permeability. Porosity is the amount of pore space or volume within the rock or the sediment that is available for water to fit. Okay, and then permeability is the ability of water to flow through that material. And so we want it to have a high porosity and a high permeability so that water can flow through and it will stay there. Okay, so in rock or soil, we're looking for pore spaces, fractures and joints, vesicles, cavities, any open air space where water can flow through. So looking at the difference between permeability and porosity, it really depends on the type of material. So if we have gravel, water can flow through gravel really quickly because gravel isn't as tightly packed. Gravel is a larger particle, and so larger particles typically have more pore spaces between them. And the higher the porosity, the higher the permeability is going to be. With clay, clay is really small particles, and so it compacts together really well, and there's not nearly as many pore spaces, so the permeability is going to be slower. Okay, so that bottom right shows you the permeability, so how fast water is moving through these different materials, and then on the left, it shows you the porosity or the pore spaces in between. And so the things that are really affecting porosity, which is also affecting permeability, is the rounding, the sorting, and the cementation. So we just looked at size. So particle size impacts porosity and permeability, but so does the sorting, the rounding, and the cementation. So if there are particles that are really well rounded, there's going to be more pore spaces in them because they don't fit in between as tightly. Think of marbles versus So the round marbles versus flat marbles. Flat marbles you can probably fit more of in a jar than you can round marbles, but you can fit more water with round marbles than the flat marbles. Flat-sided marbles anyway. And then sorting, if we have a bunch of particles that are all the same size, so let's take a bunch of round marbles in a jar again, you can fit quite a bit of water in there. But if you take the same round pebbles and then you also put sand in there, you can fit less water. And then cementation is also really important here because if the rock is really well cemented, there's not as many pore spaces for water to fit. So we want something that's well-rounded. We want to see something that's well-sorted, and we want to see something that's not cemented in order to fit a lot of water and be able to infiltrate. All right, so just to summarize the surface water, water is essential for life. Only 1% of Earth's water is usable. Surface water is water that flows on the surface of the Earth. We're looking at braided streams and meandering streams. Braided streams are networks of channels with high sediment load. Meandering streams curve through the landscape, and we see 4 drainage patterns here: dendritic, trellis, rectangular, and radial. And then infiltration is essential for recharge of our groundwater systems, which we were going to talk about in the next lecture. I will see you guys there. Bye.